Hello, this is Concrete Path and second lecture for your RCC. That's limit state method. That's limit state method. Limit state method. So this is our main topic for today's lecture. And before that, we have two more methods of design. So there are two more design philosophies. So we are going to get an overview of those also. So first one that we call as WSM, working stress method. Working stress method. That we say that this is your conventional method of design. That's working stress method. That's conventional method. Conventional method. And it talks about that material behaves in a. It says that material behaves in a linear elastic manner. Material behaves in a linear elastic manner. Behaves in a linear elastic manner. Linear elastic manner. That means the stresses should be such that they are lesser than the permissible stresses. So such stresses in the material, they should be lesser than the permissible stresses, sigma p. So we say that what is sigma p actually? We say sigma p is sigma permissible. That's actually equals to your strength of material divided by factor of safety. There is some factor of safety we have applied on the strength of material. So we say that the sigma permissible should be such that we have some strength of material. Let's talk about that. If I take first material that's your concrete, I would say what should be the sigma permissible for your concrete? I would say it's having some FCK, characteristic compressive strength, divided by some factor of safety, and that factor of safety we have here, that's multiple, that's having value of 3. So overall permissible value of stresses in concrete should be equals to 0.33 FCK. So we say that in this WSM it says that your stresses in the material, your concrete material, that should be lesser than 0.33 times FCK. And similarly for second material, that's your steel, it says that sigma permissible for the steel, that's equals to its yield strength divided by factor of safety, and your factor of safety for the material is 1.8, and your permissible value equals to 0.55 Fy. So that means sigma developed in the material, sigma in the material should be lesser than 0.55 Fy. So these are the this is your first method, that is working stress method. So it applies factor of safety on the strength of material itself. Now it does not encounter the that factor for loads. It does not talk about the loads. It talks about the material. It says that I want my material to be under less stress condition. I don't want that it should have gone beyond that strength of material. So that's your WSM. And based on this assumption, we can see that your material, your steel, we say that the stress should be lesser than, even lesser than the 1 by that's almost 0.5 of your yield strength. So lesser, we are using that steel lesser, under utilization of material. Similarly for your concrete also, you are not using that strength. So we underestimate, you can say we can underestimate the strength. So we underestimate the strength of materials, underestimating the strength of material. And based on this, we say that your design sections, the sections which you are designing, design sections become thicker. So you need a lot of material for a particular kind of load, for particular moments and extra, all of that. You need you need a section that's having dimensions bigger. So that means your structure is uneconomical structure. So this method is that uneconomical structure. So it would ensure safety and serviceability. Undoubtedly that your safety and serviceability is ensured. Serviceability is ensured in this method, because your sections are thicker, and your stresses are in the material are lesser than your strength of material. So they are showing that safety and serviceability. but your design is that what you call as uneconomical. Second method we have, but we say that we don't use this method for this date, but in some cases we are going to use we are still going to use this method WSM. So we say that WSM is still using, it has been under use for the design of first one is that one is your water tank, and next one is that RCC bridges, and third one is that design of chimneys, and the code that are used for these three, that is your IS 3370. This one is your IS IRC 112, and third one is that IS 4990, 4998. So these are the codes that are used for these particular what you call as particular structures, and so we are going to use that WSM for these structures. But for your general RCC, that's beams, slabs, columns, so we are not going to use that WSM. So we have that limit state method here. Now second kind of method is that what we call as ultimate load method. ULM, ultimate load method. This is the second method. So it was introduced in 1960. So it says that I'm not going to apply those factors, that safety factors on material. I'm going to apply factors on loads. So I would say if my working load is there, some working load is there, so that should be equals to some total collapse load divided by some load factor also. So it talks about the loads. It says that if the curve is there, let's say there is some steel, let's say some general steel is there, going only up to Fy, I'm going to up to ultimate level. I'm going to going up to ultimate levels because of these loads. I want that collapse. I am reaching up to collapse. That's why this one is your ultimate. So it tries to reach to the ultimate level of that material. So it says that our working load should be such that if I am applying so peak collapse would be such that it would cause that collapse of the structure. But based on this method, you say you don't go to full entirely collapse. You should go to some working load. That means there should be some factor associated with that load. So that's why your load factor is there. And it says that I am going to use that material even on the non-linear part of the curve also, So it tries to use the material fully. It tries to utilize the material fully. It tries to use that material fully. So but once it goes to the extreme level, one thing is that happens here is that your sections become thinner. That means it's trying to use the material fully by applying those factors, load factors. Thinner sections are developed. Once your sections are thinner, there's a chance that your serviceability is not ensured. We will say serviceability is lacking. It does not talk about serviceability. Maybe the structures might be economical as per the safety point of view. I would say that strength point of view, they are economical, but your serviceability has been lacked. So your serviceability is not ensured. Serviceability is not ensured in this method. Now third one is that what you call as limit state method. So limit state method is an rational method. Over the other two, this one is your rational method. So it talks about that. I want safety. It says that I want safety at collapse loads, or we can say ultimate loads, and serviceability at working loads. working loads. So it ensures that both of the things, that serviceability and safety, by at two different levels. So uh, this method is applying factor of safeties. Factor of safeties are applied on material, and one is that factor of safety is applied on loads also. So because of this, since other two methods were applying loads factors on either of the loads, either on loads or either on the material strength. But this method is your limit state method. It applies that factor of safety for the and both of those two criteria. One is your material and next one is that loads. So factor of safety for material and factor of safety for loads. Based on this, we say we call that those factor of safety as partial safety factors. That's why we call here as partial safety factors. Partial safety factors. So some factors are applied on material and some factors on the loads. So partial safety factors. Partial safety factors. So it says that that if your limit state is there, that means there is some state in the structure that has occurred. If this limit state occurs, if this some state in the structure occurs, if this limit state occurs, that means the structure is not fit for use now. Fit for use. So we have two different states of that. We have two different limit states. One is that limit state of serviceability and limit state of collapse. So either of the two, if one of the two or both of the two has reached, that means if the limit state has reached, that means your structure is not going to be used then. So it has been, I would say, it is unfit for the design use now. It's unfit for the use now. So this method is saying we have two different states of that limit state. I would say one is that limit state of serviceability, and second one is that limit state of collapse. So first one is that we are going to say limit state of collapse is limit state of serviceability. It was this method is saying that I want serviceability at working loads. So it talks about that serviceability at working loads. That means it's saying our structures should be serviceable at working loads. They should give satisfactory performance under working loads. Now there are few terms that are related here with that limit state of serviceability. It accounts that what we call as deflections. It accounts that cracking, or we can say crack width. One is that vibrations, deflections, crack width. Any other thing? Leakage. So these criteria are associated here with that limit state of serviceability. So these things we have to ensure that they are not going beyond that limits we have. There are some specifications or limits. So our serviceability criteria is that your permissible deflections, because of the loads should not be greater than the permissible deflections you have. So that means these are related to the discomfort, maybe, or we can say comfort. So they might be causing discomfort to the observer, or to the one that's present in the building, or going under the structure, at the structure. So there might be discomfort. There is a discomfort with the structure. So crack width, we have to ensure that it's not more than the what you call as permissible values. The vibrations should not be there. There should not be leakage. Let's say there is a water tank, there should not be leakage, or there's your bathrooms, etc. There should not be, the walls should not be such that there's leakage. And similarly, deflections, your deflections is, that means you would see your slab hanging under your head. It's trying to have a sagging curvature, and you are going to see that with your naked eyes. That's very crazy, nah? That's very crazy. So this one is your limit state of serviceability. And second one is that limit state of collapse. Limit state of collapse is having, it accounts that limit state of flexure, compression, and one is your torsion, and one is your shear. So based on these four, we have 4 chapters related to your RCC. So we had 4 different chapters related to that limit state of collapse. One is your limit state of collapse in flexure, limit state of compression, limit state of torsion, limit state of shear. So based on these 4, so we have to ensure that we have to ensure that there is sufficient strength in the materials, and there's no overturning. There's no overturning of those structures. There's no overturning, sliding, buckling, fatigue of the material. So these things we have to ensure in the limit state of collapse. So we got this one. Now one point is there. We say if your structure has reached, I would say, if your structure reached limit state of serviceability. Now one more thing is that if you try to remove the loading, if you try to remove the loading, that's unloading, we can say. If we remove the loads, that means we say that under this condition, that serviceability condition, your structure is going to come back to original position. Original position is achieved. Original position is achieved. Comes back to original position. Structure comes back to original position. Structure comes back to original position. Okay, but it is not true for your limit state of serviceable collapse. Once it has reached that limit state, so I would say it would never come back to your original position. That's your criteria, that limit state of serviceability and collapse. Now we are studying now limit state of collapse, limit state of that we have limit state method. So now we have first topic, that's your limit state of flexure, limit state of collapse, and in that first one is that flexure, that's your bending flexure. Now it says that first one, that's your characteristic strength of the materials. So I would say your limit state is applying those factors, partial safety factors, on both materials as well as on both loads also. So first one is that characteristic strength. So this is talking about the material characteristic strength. If you say I want to talk about concrete, I would say then we have characteristic compressive strength, that's your FCK, and that we know that's equals to Fm plus 1.65 sigma, and the definition we already know that this is that value of strength below which only 5% of the test results are expected to fall. So this is your 5% of the test results are having strength lesser than this value of FCK. And similarly, if you talk about that, what you call as steel, for the steel we say your characteristic strength is equals to yield strength for steel. This one was for your concrete. Now second one is that once you got the material, now we are going to say one more thing is that characteristic load. So we have characteristic load. So what do you think that characteristic load is all about? So that we represent by F, and the diagram we are going to show by this way. So So it says that this is that value of F, that value of particular load, which is expected to occur only 5% times in the lifetime of the structure. It's going to come only in 5%. That's total probability of that load is 5% in the entire lifetime of the structure. So that we say probability of what you call load has 95% probability of not being exceeded during the life of structure. So that means if your structure is there, we would say there's some value of F such that it won't be coming more than 5% time of the life of the structure. If the life of structure is 100, so that means only 5, let's say 500 years. So I would say uh, the probability of that, let's go for the definition and you can get the definition. So I would say character load has 95% probability. Load has 95% probability of not being exceeded during the life of structure. So that we have that I would say if you represent the probability here, I would say there's only 5% probability that this load has been exceeded. If there is some value of F, I would say that value of F is equals to some mean value of load plus 1.65 sigma. 1.65 sigma. This is your 1.65 sigma, such that this probability is only 5% that more than this, that this particular load would be achieved only 5% of the lifetime of the structure. Okay. 90% probability of that load not being exceeded during the life of structure. Now the thing is that we have that confidence limit. So it's similar to that in the concrete. We say that FCK equals to FM plus 1.6 minus 1.65 sigma. And in the what you call as loads, in the loads we say that there is some F that is equals to F mean plus 1.65 sigma. And similarly, if you go to some value of F such that that is equals to FM plus 1.65 sigma, that means on the right side of the mean there is some value of F that's at 1.65 sigma times that from the mean. So these two limits we call that as confidence limit. Similarly, in this case, if you go to 1.65 sigma, and from the other side if you go to minus 1.65 sigma from the mean, you have these two different limits. And I would say this limit is saying that we have that most of the results are in this range. Most of the results are in this range, So there is no use for us now. So we say that this is your what you call as confidence limits. If you say what's the total percentage of those specimens in this range, I would say this was your 5%. Similarly, from the other side, this is your 5%. I would say 90% probability is there that 90% of the specimens would be having under these two limits, confidence limits. Okay, let's go for that. Once we talk about that material strength, characteristic strength, then we say that we are not directly going to the characteristic strength, where we are applying some factor of safety here. So for that's why we say first one is that partial safety factors for materials. And that we can write gamma ms for materials. This is a partial safety factor for material strength. Gamma ms. If you talk about what you call as steel, gamma s for steel, that's equals to 1.15. And if you talk about for the concrete, that's 1.5. And initially, if you say what was the value of that gamma, or we can say factor of safety for the steel in the WSM, it was 3, it was 1.8, and for the concrete it was 3 times. So it has reduced to 1.5, and this one is your 1.15 for this was in the case of WSM, and this is your LSM, and it has reduced those materials factor of safety. Here we call it as partial safety factors. Okay, now based on this, can you get the design strength? Can you get the design, what you call as design strength of materials? So based on this factors, we say that there is some design strength of materials. Design strength of materials. So we can write first one is that F that's your F design, that's your characteristic compressive strength for divided by factor of safety. If you talk about concrete, I would say FCK by that factor of safety, gamma MSC, that's your factor FCK divided by 1.5. So it comes out to be 0.67 FCK. 0.67 FCK. So this is your design strength for the material. And second one is that if you talk about the that design strength for the steel, and that would be equals to your yield strength divided by factor of safety, that's your partial safety factor 1.15. So it comes out to be 0.87 FY. 0.87 FY. So 0.87 FY. And the reason here that why larger value for concrete, why bigger factor of safety for your what you call as concrete, I would say because of more non-homogeneous behavior. So it's because of its non-homogeneity, you have that concrete having more variation in strength, That's why we apply that factor of safety, more variation in strength in concrete. So so this is actually all those materials in the world, they are all non-homogeneous, but you compare the steel and what you call as concrete, and I can say that steel is more homogeneous with respect to that concrete, and we make the steel in the factory that's having good quality control as compared to what you call as concrete that may be having under poor quality control. Now we got this partial safety factor also. Now talking about the loads now, let's talk about the loads now. So we had different load combinations. We had two different load combinations, and based on the different load combinations, we had different factor associated with those loads. If the first load is that if there is dead load only and if there is live load only, if these are the two loads that are acting on the structure, let's say a live load would be, let's say there is some building, small building, there's dead load of the structure, and there we have some moving live load also. So I would say this is your dead load plus live load combination of the structure. And for the both, we apply factor of safety, that's 1.5 partial safety factor for the both ones. So this is our first load combination, and we apply this factor of 1.5 times that. This is the case. This is the case for, let's write it separately so we can have a clear picture for that one. So this is the load combination from this side, and after that we say there is some limit state of collapse, and from the other side we say there is some limit state of serviceability. So in this case we say, if the first case so first case that if your combination is dead load plus live load on the structure, I would say you have to apply the factor of safety equals to so we have to apply factor of safety, that's 1.5 times dead load plus live load. And the second combination is that if there is dead load and there is wind load, or we can say there is earthquake load. So we write that wind load or earthquake loads. So we can write wind load or we can write earthquake loads. So out of those two, there's the maximum out of those two, we have to keep that for the calculations. Out of those two, we have to keep that in the calculations. So we say if there is dead load and there is wind load or earthquake load, and we say your factor of safety for the both materials is 1.5 times that dead load. Sorry, for not for materials, for the loads, dead load plus live load, 1.5 times. And sometimes we multiply that 0.9 times dead load, and this one is your 1.5 dead load. Sorry, this one is your wind load. This was your wind load. Okay. And third combination is that if there is dead load, there is live load also, and there is wind load also. That's sometimes there might be earthquake load also. So if all those three combinations are there, we say the probability of all those different combinations arising together, that's lesser. So we have this factor that's 1.2 times only. So we say that there's factor of safety only, that partial safety factor for loads only 1.2, dead load plus live load plus wind load. But on the other side, if you talk about serviceability, it does not apply the loads on the materials on those loads. It simply says under the working loads, we are not going for the that safety criteria. We are going for the serviceability. That's your under what you call as working loads. We don't care about that uh, factor of safety. We say that there's simple load that's acting, that's serviceable loads, working loads. So we apply only 1 times factor of safety. That's 1 times dead load plus 1 times live load for all those cases. So this is your 1.1 times dead load plus 1 times wind load. And in this case, we say there's dead load plus 0.8 times live load plus wind load. So our main goal here is to get the most out of this combination and these two combinations. So we are going to use this one as your most frequent used. That would be most frequently used in the problems. That's your 1.5 dead load plus live load. 1.5 dead load plus live load. So this 0.9 is sometimes used when there is stress reversal. When there is stress reversal, that is possible because of the action of wind. There might be sometimes wind in one direction and sometimes in the other direction. So different possibilities are there for those wind loads or earthquake loads. That's to and fro. That stresses change. Initially, that if you are designing structure in that for this loading in this direction, so I would say this is some tensile section, and from the other side there's compressor side, but sometimes the loads would be in the opposite direction. So we have to balance those two different combinations here. So based on this, we have to ensure that sometimes there is also what you call as overturning. Overturning is also there. Overturning can be also possible for those structures. So we apply that 0.9 dead load time at that time. So this 0.9 is applied. 0.9 dead load is used when there is possibility of stress reversal and there is possibility of overturning of the structure. For that structure, we are going to use this 0.9 dead load plus live load, 1.5 times wind load. Okay, so let's get the thing that finally the most important for your RCC one. That's your 1.5 dead load plus live load. Okay, let's go for that one. Now let's go for one more thing. That's what we call as strain in concrete. Let's come to our main topic for your limit state of flexure. That's your strain in concrete. Let's talk about strain in concrete. Once you have performed the test on the cylindrical specimens, so we got the stress strain curve. So there is some stress strain curve on the cylindrical specimen. You have performed the stress strain curve test. So we got that curve. Let's say the curve looks like in this way, and we know that peak is observed at 0.2% strain, 0.2% strain, or 0.002 strain. So corresponding to that, we have some compressive strength of Fc, And we say that if the load is actually if the column is actually loaded, or we say if the concrete specimen, cylindrical specimen is actually loaded, we say that the strength, ultimate strength or compressive strength is achieved at 0.2% strain. Okay, that we already know. At this strain, your that ultimate strength has been achieved for the concrete. And one more thing is that we are going to assume one thing. We are going to assume one thing based on those facts, that when you perform the test on different grades of concrete, we have this one is your fixed value, this one is your fixed value, that the peak was observed at 0.2% strain, but your different values of what you call as crushing strain, can we call it as crushing strain, at the point where curve ends, so it was varying in some range. And then finally we say, for the design, we say we are going to assume one of the values as 0.0035. So we are going to assume that 0.0035 strain here at the end. We are going to assume that we have a particular value of 0.0035 strain at the end. That means that if you talk about that flexure, once we are studying that flexure, that's bending moment, applying the bending moment, because of that we have tensile and compressive. So we say that in the flexure, we are saying that your strain in the concrete should be 0.0035, such that your crushing of the concrete is going to happen. For the crushing of concrete, we say your strain should be assumed to be 0.0035. That means your that on the top side of that compressive side, there should be that value of strain equals to 0.0035, such that your concrete is going to crack. Concrete is going to crack under flexure. So this is your strain in concrete. Now we are going to assume, we have few assumptions in the limit state of flexure, and after that we are going to derive a few equations, and that's how your design of beams is going to be happening there. Let's go for those limit what you call as assumptions for limit state of flexure. So let's write that that what we call as, let's write that assumptions. We have assumptions in limit state of limit state of flexure. One general assumption always you can have, that's plane section remains plane. Plane section remains plane even after bending. Initially the section was plane, and then after bending it remains plane after bending, or we can say flexure. So that what that infers, what we can infer from that, we say your strain is linear, strain variation is linear. If there is neutral axis somewhere where strain is 0, this is the locus of those points where your stress is 0, bending stress is 0, or we can say strain is 0. So once you have some neutral axis, and I would say you got some value, particular value of y from neutral axis above or to the bottom side. So I would say at that particular location, what is the strain at that location y, that is proportional to that particular location y. So that's your strain proportional to the distance of that fiber from the neutral axis. So that's your plane section remains plane, and before and after bending. So that's your strain at particular location is proportional to the distance from the neutral axis. And second assumption is that we say that maximum strain in concrete. So we say maximum strain in concrete at the outermost fiber is equals to 0.0035. So once we have that diagram of that strain variation, we say that in the positive side, that is called compression side, for the sagging bending moment, I would say that maximum strain in compression side of the compression side. So I would say maximum strain in concrete in the compression side. So that should be equals to 0.0035. That means on the top extreme fiber for sagging bending moment, for top extreme fiber, your strain in concrete should be equals to 0.0035. This is your assumption 2. This is your assumption 2. Third one is that uh, third one is that third one is that once we got the what we call as stress strain curve, we saw that stress strain curve for the concrete. It was some fashion, it was in some sort of fashion in this way. Then we assume it in this fashion. Let's see how we assume that. We say that up to the peak value, up to 0.2% strain, we say that the variation here is parabolic. This is a parabolic curve. Parabolic. We assume that this is parabolic, and similarly we idealize it to a curve that's also parabolic up to this strain. So this is also parabolic, we say. This is also parabolic. And after that we say your this variation is not there. We say we are going to keep it as a straight line up to the strain value of 0.0035. So this is your idealized that what we call as idealized stress strain curve. Idealized stress strain curve for flexure. Stress strain curve for your compression test that was performed on the cylindrical specimens. Idealized stress strain curve. Now thing is here. Let's talk about this one. That third assumption, that once we assume it, variation in this way, that initial part is parabolic and after that we have rectangular. It's saying that we can assume it in this way also. We can assume it in this way also, or we can make it as a trapezoidal also. We can make it as a trapezoidal also. We can make it as a rectangular also. But the thing is that we have to ensure that overall results should be in agreement with the test results. So we have to ensure that overall that results you derive out of this any curve you assume, you can assume out of these, you can assume out of all those four, you can assume any of those four. You can either assume this one, or this one, or this one, but your results should be in agreement with the actual test results. They should be in agreement with the test results. So based on this, we will be having two problems that we are going to change that diagram. We are going to see one of the problems related to this one, but for the derivation we are not going to keep this one, but a problem would be also dealt with this form of that stress strain curve. So for the derivation we are going to have this one, that's almost equals to your actual stress strain curve. So this was your actual one, and we are going to idealize it for our derivation. This was for your derivation. This is, we idealize it in this way. That's your stress is constant after the strain value of 0.2%. So this initial part is parabolic. After that we have derivative, that what you call as straight line. Okay. So if I say that this is your actually what you call as, so this is your test, this is your stress strain curve. Let's try that this is your stress strain curve for compression test. Actually it is for compression test on concrete. Compression test on concrete. And one more assumption would be here. Then after that we are coming back to this one. Let's keep it for some time here, and let's go for one more assumption. One more assumption is there. One more assumption. That's your assumption number 4. Assumption number 4, that's saying that tensile strength of concrete is ignored. Assumption 4, tensile strength of concrete is ignored. Tensile strength of concrete is ignored. We already know that concrete was your brittle material, so we had to add a reinforcement of steel such that it can take the tensile loads. That steel would be taking tensile stresses, and similarly we say that we are going to ignore the strength we can have from the concrete. So there might be some strength that your concrete can deliver. We have already know that. Let's talk about FCR. That was your 5000 root FCK, but we are not going to use that part also. We're going to say there's no tensile strength anything associated with concrete. We are going to ignore fully and fully. We say that all those tensile stresses are taken by steel. That means all tensile stresses are taken by steel only. Tensile stresses by steel only. Steel only. Now, if I have a section, let's say I have a section, and uh, I'm applying that sagging bending moment, M sagging, and I know that strain variation would be on the top side we have compressive strains. Let's write that as positive compressive strains, and from the bottom side we write as tensile strains, and similarly we have compressive stresses and compressive tensile stresses, compressive stresses and tensile stresses. But once we say that we are going to ignore, see here we have concrete in this beam section, we have concrete. This is your concrete. Okay, then after that we say that on in the tension zone we are going to use that what you call as steel. Let's say we have some bars here, steel bars. This is your steel on the tension zone. This is in the tension zone, okay. Now based on this assumption we say your concrete in the tensile zone, tension zone, that's not going to take any stresses. Once this we say if the area below the neutral axis, that's your area of concrete, that means we are going to ignore the entire area of the concrete in this region and only keeping those bars of steel here. That means we say that actually it would be some fashion. They actually assume that there is no beam anywhere there, only at this level, at the level of those steel bars. At the level of steel bars we say there is some tensile force that has developed, or we can say tensile force resistance had developed because of the section that is taking some tensile loads. That tensile loads tension that's equals to 0.87 Fy AST. That means it does not talk about what you call as concrete here. So entire area of the concrete has been unutilized here. So that because of this assumption that we are going to ignore the concrete tensile strength, only taking the that strength that is developed because of the steel. And from the top side we are going to say your concrete is going to take the compressive loads. That means above the neutral axis we have compression zone. So all those compressive loads will be taken by the concrete. Let's have that also. Now we are going to say what should be our profile here, stress profile. What should be our profile here? And for that we have to go for the stress block. We have to go for the stress block. We have to go for the stress block. We're going to see what should be our profile of that stress block. Now this was your, if you see this one, this is actually as per steel. If you talk about strength of material, we say that there is some bending stresses, and the variation is in this way, that sigma by y is equals to m by I equals to E by R, and we know that stress proportional to strain, and because that strain was proportional to strain, stress was proportional to strain, so we used that this was your variation of those stresses along the depth. And for the concrete here we are going to take that what should be the strength, that is the resistance of that section, and for that we have to go that what should be our block here, what should be the variation here. For that we have to go to our concrete brother. That's your concrete brother. It's saying that the curve we have here, this curve, this sort of curve. So this sort of curve we have to utilize this curve here. See, when we talk about strength of material, that's your structural analysis also. If we talk about strength of material, we have that we say that our stresses are below the yield stresses. So the curve actually for the mild steel it was in this fashion, but we say that our stresses are only in this part, in the linear part. That means we say that our stress strength curve is actually in this fashion. So this is our strength of material. It talks about those smaller deformations in the structure, small deformations of elastic deformation. That means Hooke's law, we say that Hooke's law is valid there. But in the concrete, because we have this concept here, we don't have this curve, we don't have a straight line curve for the concrete. We have this curve, what you call as parabolic variation. Wait, because the concrete, it's having let's write it, because the concrete is having non-linear stress strain curve, non-linear stress strain curve. And based on this one, our stress diagram is not in this fashion, so stress diagram has to be changed according to stress strain relation. So once we got that strain diagram, once we got that strain diagram, okay, this was your strain variation, and we need to get stress variation. What should be the stress variation along the depth of the section? Along the section, what should be the variation of stress? So one of the assumption is that below the neutral axis we are going to ignore the concrete strength. So that means only at some particular depth, somewhere here, there is some tensile force acting on the section. That's tensile strength, that is the resistance of the section towards tensile stresses. So that's all taken by the steel. Okay, and its value is we got it here. Let's forget the value. There's some value of tension here. And from the other side, from the top side, we have to see what should be our diagram for the concrete. What should be our diagram for the concrete? So from the top side, we say your stress strain diagram is in this fashion. So we have to make same sort of stress block for your concrete. That's your compression zone. So same sort of curve has to be used for this case. I would say corresponding to the maximum strain that's in the top extreme fiber, that was your 0.0035. This is as an assumption 2. You can see that assumption 2 is saying strain is on the top compression fiber is equals to 0.0035. And from the diagram, can you tell me where this value of is in the stress strain curve? And that value, I would say, that's at the extreme. That value is at the extreme. And from this value 0.0035, corresponding to this strain, your stress is this much. So this much is your stress in the concrete. This much is your stress in the concrete, sigma. Let's say this is some sigma. Let's say there is some sigma. So I would say corresponding to this strain of 0.0035, we have some stress of sigma. Let's try that. We have some value of sigma. After that, we say that your up to this value of strain, so that means even by decreasing strain, your stress profile is almost constant up to the strain value of 0.2%. So that means your diagram is constant. Stress diagram is constant up to some value. Stress diagram is constant up to some value of what you call as if the strain here was, let's say if this was your strain diagram, here the strain was 0.0035, and up to some value of 0.002, up to this value of strain 0.002, your diagram is constant. And after that, we can see your variation of that. That means once the strain is from 0.2% to 0, your variation is parabolic such that it goes to 0 finally. So this is your variation. That's parabolic variation. After that, parabolic variation. So after that, we have parabolic variation in the stress block. So this part we call it as stress block for the beam, stress block. So finally, I would say your stress is going from some sigma value to finally decreasing in the parabolic nature after some value of y. So this is our stress that we call as stress diagram for the RCC, stress diagram for the RCC. This stress block we have derived, that the stress block we derived here. We derived it based on the other assumptions we have, based on the assumption 2, based on the assumption what you call as assumption 3, based on the assumption number 4. So based on these assumptions, we have derived this stress block. Okay, now fifth assumption is that, let's talk about the fifth assumption, and that's saying that about the steel. Let's talk about the steel now. Let's talk about the steel. Fifth assumption. So let's talk about the first thing. That's fifth assumption is about steel. Now, if you talk about the mild steel, do you know the actual stress strain diagram for the mild steel? That is in this fashion. So this is your mild steel, mild steel, mild steel, mild steel. Okay. Now we idealize it. We idealize it according to. We idealize it in this fashion. We idealize it in this fashion. Now we're going to idealize it in this fashion, and and for the high yield strength bars, for your that HYSD bars, we know that the variation, because they don't have a definite yield point, so the curve for them, stress strain curve, is in this fashion. That's for both those what you call as FE415 and FE500. For those two, we have this curve, and corresponding to the proof strain of 0.2%, we draw a line parallel to what we call as initial slope, and this stress corresponding to that that on that particular that diagram, the intersection point of that line, that point gives you strength of Fy. And finally we idealize it. We say we keep it as it is. We keep it as it is. We keep it as it is. So now one more assumption is that assumption number six. That's your that strain in the tensile bars at the failure should not be lesser than strain in tensile bars. Those tensile bars, that should not be lesser than 0.002 plus 0.87 Fy by ES. 0.87 Fy by ES. 0.87 Fy by ES. Okay. Now, why this 0.87 here? Why this 0.87? Why this 0.87? Now, actually, this is the assumption. If you substitute the values, I would say why after that I'm going to say why this has happened here, how this has happened. If you substitute the values here, if you substitute for mild steel, and one more is that F415 and 500. If you substitute the values of Fy here, and we know that for all grades of steel, your modulus of elasticity is, we assume that is 20 to the power 5 megapascals. You substitute that value and value of Fy as 250, 415 and 500 for the three cases, and you would get a value of strain. That means strain should be greater than that particular value of 0.0031, and for the second one that should be 0.0038, and for the third case that's 0.0042. So our goal in see what's the goal here. Our goal here is, in RCC we want that full utilization of steel. We want material, that most costlier material, that is your steel. We want to utilize it in an effective way, and for the effective way to use that steel material, we have to develop the stresses in the steel up to the value of yield stress or more than yield stress. We have to ensure that yielding of the material of the yield what you call as steel should be happening there. And for that, how can steel reach to the stress value of yield stress? Corresponding to that, there should be some strain associated up to that limit. So because we have stress and strain, if there is some stress and there should be some strain, so if I want that material should go up to the yield strength, that means I have to ensure that material should go some strain, it should develop some strain. That means there should be some deformations developed in the steel also to reach that state of Fy. Okay. Now here what we have, we say that how this strain has developed here. 0.02 and 0.87 Fy by ES. If you see this diagram for your high HYSD bars, we say that up to this value, we have 0.2% strain. And after that, if you tell me what is the strain corresponding to this yielding of material, at this point we have reached to the yield point of the material. And after that yielding of the material would be progressing. That yielding of the material would be progressing after that. So I would say there is some one more value of strain here, and that value would be equals to, actually it would be equals to Fy by Es. Would that be equals to Fy by Es based on the slope? If this is Es, I would say this strain here is equals to Fy by Es. Can we say that? But this is actual. But once you design, we are talking about limit state method. We are talking about limit state method. So we already talk about that design strength. We already talked about design strength. So based on that, once we applied that factor of safety of 1.15 on the steel strength, that is strength of material by what you call as partial safety factor. So we achieved that value of 0.87 Fy. So we had to go only to some 0.87 Fy. So if this was your actual curve, after that we had to apply factor of safety such that I am reaching to some 0.87 Fy stress. So if this was Fy and this one is 0.87 Fy, and corresponding to this value, I would say the strain here is actually, this value of strain would be only 0.87 Fy by Es. So this value would be only equals to 0.87 Fy by Es. So this was the equation that's from the IS code. That's the strain in the bars should be more. So we want that yielding should be in the steel such that it has developed some stresses greater than or equal to yield stress. So I want that material should be undergoing those yielding of the material. There should be yield stress developed. So for that, strains should be at least this much amount of strain should be there. Now, based on the calculations, we got that strain in the mild steel should be up to this one, should be minimum value up to, that means minimum value of strain should be this much in the steel. But what about that what you call as mild steel? But the mild steel graph is not in this way, that it's having that, because your mild steel is having a definite yield point. You can observe that this is your yield strength, and but still we are going, but your IS code still does not differentiate that. It says let's keep that this equation for all those three what you call as all those three grades of steel. What that means here is that it, since your diagram for the what you call as mild steel is that to reach this yield stress, to reach that value of yield stress, it does not need that 0.2% strain. It does not need the 0.2% strain. That means from the initial portion of stress, it's going to develop that particular relation between stress and strain, such that I would say this strain value would be equals to that sigma yielding divided by Es. So you only need to get this amount of strain in the mild steel, so that the mild steel is going to yield. If I see what is that particular value of sigma y by Es, for that I substitute that value of sigma y is 250 megapascal, and divided by 2 into 10 to the power 5 megapascals, and that's the strain. What should be that particular value of strain in the mild steel, at which your yielding of the steel is going to be happening. Okay, and but one more thing is that we since we are not talking about real, we are going by some factor of safety, because we are talking about design strength. So we have that factor of safety also. So we write your strain equals to 0.87 Fy by Es. So similarly, on the design curve, the design curve would be some sort of, if this was your actual value, if this was your sigma y Fy, that means we are applying some factor of safety, that's 1.15, such that finally your this value would be equals to 0.87 Fy, and corresponding to that we would be having some strain, that's strain 0.87 Fy by Es, and that value is only how much, 0.00109. That means even on the strain value of 0.00109, your mild steel is going to yield, but your code that says that once your mild steel has reached to this value of strain 0.0031, that is more than 0.001109. After that, your steel is going to yield as per code. So that means that code is saying we are going to use the material, we are going to use the ductility nature of that material. We are going to use that material in an efficient way. That's why it's saying that we keep that same diagram for all those three grades. That means we assume that we assume that all the grades of the steel are in this fashion. Even for the mild steel also. Even for the mild steel, that means to get the most out of the mild steel, where we want to say we are keeping the strains up to 0.0031 in the steel, 0.0031 in the steel, mild steel. So this was your general what and what not for those assumptions of flexure, and now we're going for the actual things we can have from that flexure. That's your problem related tasks. Let's go for that. Once we have those assumptions, let's make that assumptions in a picture now. Let's make the assumptions in a picture now. I would say there's some neutral axis. Okay, there's some neutral axis, and there's some strain value of 0.0035 at the top extreme fiber as per assumption 2. And based on that, based on the diagram of stress strain curve, we had assumed that variation is in this fashion, that parabolic and after that rectangular, parabolic and rectangle. So up to the strain value of 0.002, we have parabolic nature for the stress block, and after that we have a constant value of that stress up to the strain value of 0.0035. At this particular value, we have that cracking of the material. So I would say corresponding to some value of y, where the strain corresponding to some value of y, where the strain is equals to 0.00002. I would say at particular value of y, I know that in the section that there would be some particular value of those that fiber where the strain would be 0.002. If on the top there is 0.0035 and on the neutral axis there is 0, that means somewhere would be some particular fiber along the section such that that strain at that location is 0.002. So let's say that that value of location is at a distance of y from the top. Okay, and from the assumption number, what you have 6, assumption number 6 says that strain in the steel from the bottom side, strain is in the steel in the bottom side, that strain let's write it as strain in the steel, that should not be lesser than, that means that should be more than 0.002 plus 0.87 Fy by Es. This is assumption 6. So this is at the level of steel. Say if you had that section, if you had that beam section, I would show that if you had that beam section, so let's say this was the level of at the top fiber, this is the level at the top fiber. Let's try to have that a bit down. Let's say that this is from the top level, this is at the top level, that that strains at the top fibers on the compression side is 0.0035, and this is corresponding to the sagging bending moment. I would say there is some neutral axis here. Okay, there's some neutral axis and we are applying bending moment that is sagging, and for that we have from the top side we have compressive, and from the bottom side we have tensile stresses. And I would say at some particular value from the bottom we have those what you call as steel bars. We had some sort of steel bars there, and at that particular location we say that strains in the steel should be more than 0.002 plus 0.87 Fy by Es. And there is some depth here, what we call as effective depth, effective cover. Here we have this distance up to the center to center of those bars, up to the center point of those bars, and from the bottom side I would call this as effective cover. I would say if if the section is having depth of D, why not keeping the steel bars at the bottom part? Why not keeping the steel bars at this part? Why not here? Why we are keeping the bars at some particular location that's at what you call as EC? Let's write that EC as effective cover. Effective cover. Why we are keeping this one? I would say this is for the reason that because your beam would be in some environment. There would be some environment there, and we are using steel. Steel is made up of iron. Iron is going under corrosion, and there's a chance of rusting of that steel. And one more thing, that there might be acidic environment, or there might be marine or environmental conditions are such harsh, such that your steel is going to be eroded or corroded, I can say. So we had to ensure that safety of that steel, safety of our most costlier material of the section. So we had to ensure that safety. So let's try that. Because of environmental conditions, and one more thing is that we want that steel bar should be in a good bond between the concrete. There should be a better bond between the concrete and the what you call as steel. That's only possible when there is more contact area between steel and what you call as concrete. Between steel and concrete. And for that you should have some depth from, you should have some concrete from the bottom side also. If you're using the steel bars at the bottom side, there is no concrete from the bottom side, so there is lesser bond developed as compared to if the bars are placed at some level from the bottom. So based on these two things, we are keeping some cover that we call as effective cover. And this effective cover is actually some clear cover plus that bar, what you have, that bar diameter by 2, diameter of the bar divided by 2, diameter of the bar divided by 2. And it can vary sometimes also, so we will see that also. So once we got that, now we are going to say, okay, let's have those. So once we draw those assumptions, this was your assumption number 2, and this one was from the stress block. So let's have this is your stress assumption number 3, and this is your assumption number 6, and let's go for the stress block. That's assumption number 3 also. So stress block is in this fashion. So stress block, we say since your concrete in the tension zone has been ignored as per assumption 4 or 5, so from the bottom side the stress block is having a 0 line. So this is your 0 line for the stress in the tensile zone. That means concrete section strength of tensile strength of concrete has been ignored. That means there is only a particular line of T equals to 0.87 Fy. This is your stresses, those design stresses in the steel, and we have some steel area also, AST, that we write as AST. That's the area of the steel in the tension zone. AST is your area of the steel in the tension zone, area of steel in tension zone. That means there's some tensile force developed. That is the strength developed because of the section capacity. This is the section capacity. So this is your T 0.87 Fy AST, and from the top side we have that assumption number 3, and based on that stress block we can have that stress block in this fashion. Let's go for that. I would say there's some value of stresses at the top, and it was constant up to the value of 0.002% strain. Up to that value we have this what you call as constant stress value. This was your constant stress value, and after that the variation is parabolic. So up to the neutral axis, variation is parabolic. This was your neutral axis. Now we need to get, I would say, the neutral axis. So based on those assumptions, we have to get these three different values of one is your that location of neutral axis that we represent by xu is the location of neutral axis. So this is our first derivation we have to go, location of neutral axis. And second one is that value of y. We need to get the value of y. That's why up to the point where your that stress is constant. We want to see up to what value of that y, up to what value of that depth your stress block is having constant stress. Okay, after that, one more thing is that we need to get what should be the uh, corresponding to the strain in the steel versus overall depth. We want to see any relation is there. So that's your third task. Let's say that total depth was capital D. Let's say the total depth was capital D, and then after that, once you subtract the effective cover, and based on that, we say that the difference of that total depth minus effective cover, that's your effective depth. So this is our D, small d. Small d is your effective depth, what you call as effective depth. Effective depth. That's capital D minus effective cover. So in the analysis, we are going to take only that part of effective depth. So if I say what is this total depth equals to, up to the level of that steel bars, I would say this depth is only equals to small d. That's actually effective depth. That's actually effective depth. And let's go for one by. Let's go one by one. 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 First one is that. Let's talk about the value of y. Can you get the value of y by the similar triangles? I would say your strain is 0.0035. It was for the length of xu, for the depth of xu from this triangle. And similarly, I want the strain of 0.002, and this was for the in the triangle of xu minus y. And once you solve it, you would say your value of y is 3 by 7 of xu. This is value of y equals to 3 by 7 of xu. That means this value equals to 3 by 7 of xu, and the rest part, that's 4 by 7 of xu. 4 by 7 of xu. Okay, now one more thing is that we need to get the value of xu itself. We need to get the value of xu. What is the value of xu? Let's go for the value of xu now. So that value of xu can be calculated from the that bigger two triangles we have. Bigger two triangles. I would say for the calculation of neutral axis, location of neutral axis, for the location of neutral axis, we need to get the value of xu. So from the similar triangles, I would say we have a strain of 0.0035 for the depth of xu. And from the bottom side, we say we have a strain in the steel that should be more than 0.002 plus 0.87 Fy by Es. And this strain, this is the minimum strain. Let's talk about the minimum critical strain. This should be minimum strain value here. And it was for the length of, what is this length total depth? What is this value of, what you can say, D? What is this value here? I would say this is equals to small d minus xu. Can we say that this part is from the neutral axis, d minus xu? And finally, from this, you solve it further, and you would receive a equation that's xu equals to that's what that we call as. Now if you substitute the value of Fy, let's forget Fy. If you substitute the value of Es equals to 2 into 10 to the power 5 megapascals, 2 into 10 to the power 5 megapascals, you get an equation that x equals to 0. Or directly we write 700 by 1100 plus 0.87 Fy. So this is our general equation, that what is the value of xu, and we have to multiply that with the depth d. So this depth d is there, and this equation is corresponding to the minimum value of that strain in the steel. We want that minimum strain in the steel should be up to this much value of strain in the steel, strain in the steel. Okay. And corresponding to this one, we say that the value here, we have this value that's a function of that is a function of this value. It's a function of, this is a function of what you can say steel. It's a function of steel grade only now. steel grade. Now we call this constant value, we can say this is some constant value k, and it depends on the value of, so there is some constant value of k that it is a function of steel. And let's have the value of k for different grades of steel. Let's have the value of k for different grades of steel. Let's say that I want to get the value of k corresponding to the Fy of 250. One more is that 250 megapascal, one more is that 415 megapascal, and third one is that 500 megapascal. If your yield strength is 250, that is mild steel, and 415 and 500, that is your HYSD bars, and corresponding to those values you can get a value. And after by the IS code says that we're going to finally make them equals to, we're going to make them equals to 0.53, 0.48, 0.46. So if you substitute the values here, 250, 415 and 500, you would get this value of 0.53, 0.48, 0.56. So these three values, these are critical values we have to use for our calculations. And actually we say that this was your XU value, this was your value of XU. Now we say this is not actually XU, this should be some limiting condition, because we are talking about that strain. Actually the strain should be more than what we have here. We say that strain should be more than, actually strain should be more than this value, but we for the calculations here we say that strain in the steel should be equals to 0.02 plus 0.87 Fy by ES. And when we say that strain should be this much value here in the top, in the bottommost extreme fiber in the tension zone, this means that we should have a section that we call as balanced section. We call that as balanced section. We will see that also after some time, balanced section. And corresponding to that section, we say that the XU changes to XU limiting. So this is your limiting condition. So based on that, we say that this value is XU limiting, not XU only. So if I calculate this equation, if I say that I'm calculating this entire thing corresponding to XU limiting, then I would say this equation we have, this is corresponding to XU limiting. This is corresponding to XU limiting condition. We are going to see that what this limiting condition means, and for now let's keep that as XU limiting equals to some KD. So let's go for finally let XU limiting equals to KD, K into depth, effective depth. So where your K is a function of steel grade, so your limiting depth of neutral axis, this is the limiting depth of neutral axis. We are going to see what this limiting means, and till now let's keep it as it's okay. Now we need to go one more calculations. We say we have not touched yet the stress block. Yet. Let's try to see the stress block now. Once we touched the strain diagram variation, now we are going for the stress block. Let's analyze the stress block now. Stress block. So in the previous derivation, we say that this value of y was equals to 3 by 7 XU, and second one would be equals to 4 by 7 XU. Now I would say there's some stresses at the top, and we need to see what is that value of stresses at the top. Let's see what should be the value of stresses at the top. Initially I said there is some sigma value here. Now we need to get that value of sigma here. What should be that value of sigma? So I would say we had concept of design strength. Did we have concept of design strength? Initially we have characteristic strength. That was your FC, and corresponding to the concrete we say there is some FCK. This was your characteristic compressive strength. And this was, we have performed this test on the cylindrical specimens of some fixed dimensions, 150 cross 300. This was corresponding to this value, or we can say this was corresponding to cube. Let's go to the general level. This was corresponding to cube. That FCK is corresponding to cube value with dimensions 150 mm cube. 150 cube mm cube. This was your cube. Okay. Now this was your size is fixed here. Size is fixed. Now in the actual structures, does the size remains as this value, total value here, and this was also corresponding to what you call as uniaxial stress condition. This was corresponding to uniaxial stress condition, that the FCK you derived from here, it was corresponding to a uniaxial stress condition and the fixed dimensions. So but in the actual structure, if there is actual structure, there is some different size, there is some different size, and there is some multi-axial loading also, multi-axial loading. So we say that because of these we have these two effects, and we had to say we have one more factor of safety here. We need to say if there's FCK compressive strength of, let's say, 40 megapascals, we would say in the actual structure we won't get exactly the same value of strength in the actual structure, because of the size effect, and because of that there won't be only axial stress, there won't be only one direction stresses, there might be multi-axial loading, combination of different loadings would be there in the actual structure. So that's why so we have that factor of safety, one more factor of safety, that's 1.5. So one more factor of safety is applied on the actual design strength. If your actual design strength was, if your actual design strength we had earlier, that was equals to actual design strength was equals to FCK by factor of safety, that's your partial safety factor. This one was your partial safety factor, and in this one we had not at that time we had not we did not say that that effect of size and multi-axial loading. Now if you're talking about actual structure, because you are designing actual beams, actual slabs and beams, you have to apply actual factor of safety also, so finally your stresses should be finally design stresses. I would say the stresses at the top most fiber should be equals to F topmost, let's write F topmost should be equals to our design strength, where design stresses should be equals to, initially it was FCK, then you divide by partial safety factor, so finally divide entire part you have to divide by 1.5, so you would get a value of 0.045 FCK. So if there was initially the graph of the stress strain curve of the concrete was in this fashion, stress strain curve, and this was corresponding to for particular size of that cube or cylinder. Then after that, when we idealize it in this fashion, parabolic and straight with the strain values of 0.002 and 0.0035. After that, when we applied that partial safety factor for material, that is your design strength finally. So this was your first effect. If this value was FCK from the top, after that you are going to FCK by 1.5, that is 0.67 FCK. And finally, if you want to go for actual design strength, for the concrete, that's for the design actual design strength, you have to apply one more that factor of safety. So that's your finally your design, your diagram is in this fashion. Such that your value here is 0.67 divided by 1.5 FCK, such that finally this value is equals to 0.45 FCK. That means if your final diagram for the stress block would be in this fashion. So with the design strength value of 0.45 FCK, and the strains, we know strains are same, 0.002, 0.0035. So this is your final idealized stress block, design idealized final idealized design stress block for concrete in compression. So let's take that now. Finally that I would say the stresses are 0.45 FCK. Stresses here equals to 0.45 FCK. 0.45 FCK. Since I would say there is some stresses on the section, and we have some section also, section area, so I would say there are some compressive forces that are developed. That means there is some resistance developed in the section. I would say the centroid for the first part of the compressive, let's say there is some C1 in this part, or let's write that C2, and there is some C1 acting here, C1 and C2, and its centroid is somewhere here, and for the parabolic part we have centroid somewhere here, and we can get the centroids also. Now we need to get those value of C1 and C2. Can you get the value of C1, C2? Can you get the value of C2? What is the C2 compressive force in the section that has developed? I would say that is equals to how much stress we have, 0.45 FCK, and that's constant for this rectangle. So what is the area of the rectangle? What is the area of the rectangle? We say that the depth we have 3/7 of XU, and what is the actual width? What is the actual width of the section? Let's say the actual width is B. This is our actual width of the section, cross section. There is some beam. There's some beam. Let's say there was some beam with some cross section of BD, B capital D, and you are applying bending moments, sagging bending moment, and because of that, we have neutral axis, we have top compressor and bottom tensile, and let's say that entire section of B width is resisting that that bending moment, sagging bending moment, and so I would say what should be the value of C2? That should be stress into area. So I would say area of the stress block into width, into width. That's your area of the stress block. This is area of the stress block, area of rectangular stress block, the rectangular part of the stress block into width, into width. So finally we got that C2, and similarly you can get also C1, and C1 would be area of the parabola. Do you know the area of the parabolic part? So that's 2/3 of that BH value of, let's say height is 0.45 FCK, and your B equals to 4/7 XU, and the width we have to multiply B. So finally we got C1, C2. Now I would say what is the total value of C? What is the total compressive force C? So what is the total force of compressive force C? That is C1 plus C2, and you substitute those values, you would get a value of 0.36 FCK and XU and B. So this is our C, total force of C, that is 0.36 FCK B XU. Now we would say why this total C is acting. Why this total C is acting somewhere. It might be acting somewhere at the resultant of those C1, C2. At the resultant of those C1, C2. And to get the resultant from the top, let's say we are going to get that value. I would say from the top, let's say the resultant is at X bar. X bar is the resultant of compressive forces C1 and C2. Resultant of C1 and C2. Resultant of C1 and C2 from the top. Let's try to calculate that value. I would say that value would be equals to that C1 X1 plus C2 X2 divided by C1 plus C2. We need to get the value of X1 X2. Can you get the value of X1 X2 from the top? That's centroid of the first compressive force and centroid of the second compressive force. So I would say your C2, where this value of C2 is acting? It's acting somewhere here at this part, at this value of y, that x1. Let's say this one is your x1, this is your x1. Let's try to get the value of x1. That is that 1/2 of 3/7 XU. So I would say once you calculated C1, C2, let's say what was the C1 value we have and what was the C2 value. Let's try to write those values separately. I would say your C1 was equals to we have not calculated those directly. Once you got the C1 and C2, you can say you have some C1 value, and you have that value of x1. You have that value of x1, and you have some value of C2. You have some value of C2, and for the C2, your centroid is at. For the C2, your centroid is at 3/14 of XU. Can you say that that's 3/14 of XU? I would say x2 equals to 1/2 of 3/7 of XU. at the centroid of that rectangle, and divided by where is the centroid of C1 acting? Can you get that value also? Centroid of C1, I would say that value would be equals to C1 is acting at one is this part, total part of that 3 by 7 xu, and after that we have that centroid of the parabola is acting at 3 by 8 of 4 by 7 of xu. So this is your 3 by 8 of B, or we can say 3 by 8 of 4 by 7 of xu, and plus you have to add that 3 by 7 also. We have to add that 3 by 7 also. So let's write that here. I would say one is your 3 by 7 of xu. After that we have 3 by 8 of 4 by 7 of xu. So this is our centroid 1, location of centroid 1 from the top, and divided by C1 plus C2. We know that C1 plus C2 was equals to 0.36 FCK BXU. And finally you would get a value of that y bar, that x bar. Resultant value would be at 0.42 xu, at 0.42 xu. So this is our equation we have. Centroid of, this is the centroid of C force. Centroid of C force from the top. C force from the top. So once we got the C1, C4, once we got the C force and we have also T force, can we say there is some internal, can we use that internal couple method? Internal force method or internal couple method? I would say if there's some C force acting at some particular locations at C, and there's one more force that's T acting, can you say there's some moment developed that we call as moment of resistance, that we call it moment of resistance of the section, moment of resistance of the section. So this is the resistance towards the external bending moments. This is the resistance towards external bending moments, towards external bending moments, M external bending moments. Because of those loadings, we have those C1 and we have that C and T acting at some eccentricity from each other that we call as lever arm, and finally that contributes to that moment of resistance of that section. This is of that particular section. And I would say from the top you had x bar that was equals to 0.4 to xu, and I would say there is some neutral axis somewhere here at a location of xu, at some location of xu, and I would say your moment of resistance would be equals to, let's say this value equals to some z, where your z is lever arm z is your lever arm. I would say your moment of resistance, either you can calculate as C into Z, or you can say that's T into Z. C into Z or T into Z. Now, I would say what should be that value of Z? If the stress block was in this fashion, let's have that block also here. So I would say now from this figure, I would say that the resultant is somewhere here. Let's say that the stress block was in this fashion. So at some location, the stress block, let's say the total C force is acting here at some value of x bar equals to 0.42 xu, and if the total value up to the neutral axis is what you call as xu, and this part is 0.42 xu, and after that I would say your lever arm is acting at some depth, at some d. Let's have that also here now. Can you get the value of now lever arm? So I would say up to this level from the top, this total depth was effective depth of d. So finally I would say z equals to d minus 0.42 xu. So finally I would say moment of resistance equals to c times d minus 0.42 xu, or that we can say d into d times d minus 0.42 xu. Now we need to substitute the value of C and T, and accordingly we can get moment of resistance. So if I substitute that, C equals to 0.36 FCK B XU, and you need to have this value of d minus 0.42 xu, and that should be also equals to 0.87 fy ast, and that's d minus 0.42 xu, because your t force was equals to 0.87 fy ast, and your c force was equals to 0.36 fck bxu. Okay, now we got this equation for the moment of resistance. So then we see that whether our moment of resistance for the section is more than or lesser than the external bending moments. So we need to say your external bending moments should be lesser than your moment of resistance. We need to ensure that your section is safe. That's your safety should be ensured. That's why we have limit state of collapse or limit state of flexure. We need to ensure that bending moments, external bending moments, should be lesser than your moment of resistance of the section. One more thing is that the location of neutral axis, actual location of axis. Earlier we derived the location of what you call as limiting condition for the neutral axis. Initially we derived the condition for limiting condition of neutral axis. We arrived to some value. We say that when xu was actually xu limiting, at that value your strains at the bottommost steel fiber, that was 0.002 plus 0.87 fy by es. That was the limiting condition. So let's try to get that value also now. So if I say actual location of neutral axis, this is the actual location of neutral axis. Actual location of neutral axis, that will represent by some value of xu, and that we can get by equating, because if your section is there, you are applying bending moments on the section. You are applying bending moments on the section, some bending moment m, and on that section there is no external force. There is no external force, but there is some internal c force that has developed, and there is some t force that has developed. If I apply that summation of horizontal forces equals to 0 on the section, I would say c equals to t. From that, I would say the value of c was equals to 0.36 fck bxu, and value of t was equals to 0.87 fy ast. This is your stress into area. This is our stress block area into this is our stress block area into width b, And then from this one, can you get the xu value? Can you get the value of xu? So I would say value of xu would be equals to 0.87 fy ast by 0.36 fckb. So this is our actual location of neutral axis. Equation for calculation of actual neutral axis location from the top. Now we need to say once we have one more condition, that's your xu limiting, that we calculated as some k times d, effective depth k times d. Now we need to compare the two, and based on these we have three different conditions that can be possible, that are possible here. First condition, that if your xu is equals to xu limiting. Second condition is that xu lesser than xu limiting, and third condition is that xu greater than xu limiting. So if I would say, if your section was there was some section, we had some steel ast, area of the steel bars was ast, and the total effective depth up to the center line of those steel bars was effective depth, that is small d, and there's some cross section b. I would say the limiting depth was such that limiting neutral axis location was, let's say this was your limiting neutral axis location, and I would say the variation of the strain was in this fashion. This was for the condition of limiting. So let's write green as limiting condition. Green is equals to limiting condition. I would say this was the neutral axis, initial neutral axis. For the green condition, that's your limiting condition. For the limiting condition, I would say at this location, from the top side we have strain of 0.0035, and from the bottom side we say that the strain should be equals to, strain should not be greater than the particular value. Strain should be equals to strain in the steel, that should be equals to 0.002 plus 0.87 fy by es. Okay, this was your actual, that what we call as limiting condition. Now based on this value of xu from this c equals to t, you would get different values. There is a different possibilities we have three different possibilities. First possibility was that xu is also equals to xu limiting. That means your xu actual is equals to xu limiting, and for that case we say the diagram is in this fashion. What that means actually, what that means limiting condition, what that limiting condition now means. So let's write that limiting conditions, limiting section or limiting condition, we also call it as balanced section. Let's try to understand what this means. We say that the we say that at the time of concrete cracks, at the time of concrete cracks in the compression zone, at that same simultaneously at that time your steel should also yield at that particular time. That means there should be simultaneous attainment of those strains. That means simultaneous attainment of those strains, simultaneous attainment of those strain values, that means attainment of EC equals to 0.0035, and simultaneously there should be strain developed in the steel equals to 0.02 plus 0.87 Fy by ES. So this means that from the both sides, that's in the compression zone and in the tension zone, both extreme fibers should be under the maximum those strain values. That means from the top side, concrete should start to get under crush. Concrete should start to undergo cracking, and from the bottom side, your steel should undergo yielding of that steel. It should go under yielding of that. Now this is what we call as balanced section. Okay. Now second condition is that, let's say that your XU was not, let's say that XU was, that means actual neutral axis was above that limiting condition. If this was your limiting condition, that means actual neutral axis somewhere above that actual, somewhere above that limiting condition. If this was corresponding to limiting condition, I would say your XU is actual, is somewhere here. So that means this one is your XU. If this is your XU actual, that means the neutral axis is somewhere here. This is the neutral axis somewhere here. And corresponding to this one, let's say that, let's keep one of the side fixed. Let's keep one of the side as fixed. Let's keep one of the sides as fixed. Let's say that the strain in concrete is 0.0035. If I keep that strain in one side same, then we need to join that up from the neutral axis. Let's have that. Let's try to have that. I would say let's try that, let's try to keep EC fixed. Let's try to keep EC fixed. Let's try to keep EC fixed as 0.0035 from the top, and we want to study what is happening. If I say this is your neutral axis now, and now this is the neutral axis corresponding to XU lesser than XU limiting, and finally I have to make a diagram that's a linear variation of strain linear proportional to the distance from the neutral axis, that's strain proportional to Y. So finally I would say the diagram would be in this fashion. So I would say your strain here, what is this value? Can you tell me what is this value equals to now? Can you tell me that? Can I say that this strain is more than 0.002 plus 0.87 Fy by ES? So let's have that second condition. If your XU was, your actual neutral axis location is lesser than limiting condition, that means corresponding to the failure strain, or corresponding to the strain in concrete equals to 0.0035, At that time, when it means once at particular time, when strain in the concrete has reached 0.0035, what is the strain that has developed in the steel? Can you see that? That's more than the needed the needed one. That's the limiting condition. So that means at that time, simultaneously, at that time, your strain is in steel is more than that limiting condition for yielding. So let's say that this one, we call this one as what you call as, this is our second case. This we call as under reinforced section, under reinforced section, under reinforced section, under reinforced section. So in the first one we call that as balanced failure, because from the both the sides both are attaining their values at the same time. So that's why we have that balanced failure. And in this one we say that the failure is tension failure. We call it as tension failure, tension failure, tension failure. Or we also call it as ductile failure, ductile failure. That means before the concrete is going to, that indirectly means before the concrete is going to reach that value of that cracking value 0.0035 strain, so steel has already gone to its yielding value. So strain in steel is already reached to the value where it can perform yielding of that section of that steel. So we would say that tension failure or ductile failure means that your steel is going to yield earlier. Your steel yields earlier. Steel yields earlier than strain in concrete is 0.0035. That means if your steel is going to yield at some time at that particular location, your concrete is not going to crack. Concrete is not going to crack at that time. It's not going to crack at that time. That we call as under reinforced section. So we, in this case, we are saying your costlier material has been utilized in a best way. So that's your under reinforced section. So this section, our code, IS code 456, it recommends that your section should be under reinforced section, such that your steel is going to yield earlier. If your steel is going to yield earlier, that means you are using that steel earlier in a better way. That means concrete is in its intact position. It's not going to fail till now, as long as the stresses are increasing, strains are increasing up to 0.0035. At that time, strains in steel was such that the steel was already under yielding. So that means we have already used that steel also. So we have not kept the steel underutilized when the concrete has crushed or it has gone for cracking. So that means this method, this case of under reinforced section is better that if you want to utilize the steel fully or in a best way, effective way. That means we want the strains in the steel more earlier. We want that steel should go under yielding earlier, as compared to that that strain in concrete should be 0.0035. 0.0035 strain in concrete means concrete is going to crack now. But we say that your concrete, we don't want concrete to crack earlier. We want steel to yield first, such that your steel gets utilized properly because it's your costlier material. Okay, that's our under reinforced section. So we prefer this one, that your XU should be lesser than XU limiting. We try to keep that XU lesser than XU limiting. That's our job. That's our job to design the section. We should keep that XU lesser than XU limiting, such that our section becomes under reinforced section. So we need to keep that under reinforced section, URS. And third case is that when XU was greater than XU limiting. When XU was greater than XU limiting. This is our third case, XU greater than XU limiting. That means, what that means from this diagram, let's say the initial case was in this fashion. Let's try to have the initial case that was corresponding to this was corresponding to what you call as limiting condition. This was corresponding to limiting condition. So this was your limiting condition. This was limiting condition. Limiting. Here the strain was 0.0035, and from this side here the strain was 0.002 plus 0.87 Fy by ES. Now we say that your XU is greater than XU limiting. So this was your XU limiting. This was XU limiting. This was XU limiting. Now we want to say we want to go XU greater than XU limiting. Let's say this is our new XU limit. XU. This is our actual XU. Actual location of neutral axis. That means actual location of neutral axis is somewhere here. Now we need to let's try to keep one of the sides fixed. Let's keep the strain in concrete fixed. Let's try to keep the strain in concrete fixed, and then finally join that. Then finally join the curve. Then finally join that. I would say from this side, this is our zero neutral axis. That strain at neutral axis is 0, and finally I would join the curve in this way. So our curve became in this fashion now, a strain diagram. So this is our strain diagram for XU greater than XU limiting. So let's write it below that for XU greater than XU limiting diagram, this is our blue diagram. And the white diagram was for corresponding to XU limiting, white one. Okay. Now the value here, we would say, what should be this value? Is it, what can you tell me what is this value? This means this is the strain in steel, and that is lesser than 0.002 plus 0.87 Fy by ES. Because for balanced section we have strains of this value, but in the what you call as XU greater than XU limiting, your strains and on the top side was 0.0035. That means when the strains in the top side of compression zone was 0.0035, at that particular location, simultaneously we have a strain in steel that is lesser than the minimum value. This is lesser than minimum value. The minimum value the code prefers. The code says that our strain should be more than this value, this critical value, but your strain in steel is lesser than the minimum critical value of the code prefers. IS code prefers. So that means this is not a better way. This is not a better approach to have. Let's try to go for that one also. I would say for the third case when XU was greater than XU limiting, this one we call as the section that gets developed. That is we call that as ORS, over reinforced section. Over reinforced section. That it means reinforcement is more than that required. This also means that AST is provided greater than AST limiting. This also means that, or we can say percentage of reinforcement is more than limiting percentage of reinforcement. That we also can say, because of the name over reinforced section, that we also can say AST should be greater than AST limiting. And from this one we also said XU greater than XU limiting, and the failure here we call that as compression failure. There is a compression failure, and we also can say that's a brittle failure. That's a brittle failure. Brittle failure. And that compression failure means that when concrete reaches compressive strain of 0.003, when concrete reaches what you call as when concrete reaches compressive strain of what you call as 0.0035 in compression zone, that means concrete has gone under cracking. Concrete has cracked at that location. At that time, what was the strain in steel? Strain in steel is lesser than the minimum value, minimum IS codal provision value, IS codal value. So that means the code does not, we say that your steel, because strain in steel is lesser than the minimum required value for yielding, minimum required value for yielding, because your strains in steel are such that the material has not been undergoing yielding. That means material is not properly utilize it. So material steel is not properly utilized. Steel is not properly utilized. So code does not recommend that steel be utilized in this case, because once your strains are lesser than the minimum value, that means stresses are lesser than the yield strength also. So that means your steel is of no use. Actually, we can say steel is of no use. We are trying to use that steel, its capacity to resist the tensile stresses. But you are saying that I am using the steel, but we are not we are not allowing. Our section is such that even when I place the steel in here in the section, even I place the steel in the section, but still my steel is not going to be properly utilized. So one is that we are placing the steel, even also we are placing steel inside this concrete section. Still, our what you call as material is not being utilized. That means there's a lack of knowledge or lack of concepts. So we need to ensure that our material we are using, that costlier material we are using, we should utilize it. Why should we waste the material by keeping that steel bar inside the section? We should utilize that material. We should utilize its strength. So for that, we should not prefer ORS. We should prefer URS. We should not prefer ORS. You should prefer URS. That's your under reinforced sections, such that when concrete tries to have a strain of 0.0035, strain in steel should be more than the that minimum value that IS code prefers. So such that your material steel is going for yielding, so your material has been utilized properly. So final crux from these three, I would say go for what you call as URS. Go for URS. Let's try to keep the XU lesser than XU limiting. I think we have arrived all those, we have got those all those stuffs. We derived all that stuff we derived all that stuff from those assumptions, and this lecture was entirely designed to understand those assumptions. Thank you for watching this lecture. I would say thank you for watching this lecture for your assumptions of limit state of flexure. Thank you.